Small electrical signals can be created fairly easily, like with these magnetic pickups. But small signals really aren't terribly useful for things like music. In order to hear them, we need to amplify them. Sometimes we need to boost it even more so that everyone can hear it. Right, but what makes all that amplifying happen? Well, you've likely heard of them before, and if you haven't, it's time you did. They're called transistors. Transistors allow a small amount of electrical current to control a much larger one. They're usually used in one of two basic ways: to amplify or to switch an electrical signal on and off. We can hear how helpful they are for boosting sound, but why are transistor switches so important? Well, you're most likely using them right now to view this here video. A computer's microprocessor uses millions of tiny transistors together to perform more complex, higher functions, such as processing and displaying video information. Impressive? Yeah, definitely. But even individual transistors are quite useful. Visually, they can be classified into two groups: small signal types for relatively low power applications, and power transistors for, you guessed it, high power jobs. Before transistors hit the scene, vacuum tubes were used for similar purposes. But tubes had some problems. They were expensive to manufacture, they generated a lot of excess heat, and they needed to be replaced pretty often. Most of the research that went into developing the transistor was actually done in search of a successor to the vacuum tube. But the actual invention of the transistor isn't quite so clear-cut. In 1926, Julius Edgar Lilienfeld filed a patent for something he called a method and apparatus for controlling electric currents. This was actually what nowadays we'd refer to as a field effect transistor, or FET for short. FETs are controlled by voltage and use almost no input current. Two types you're likely to run into are the JFET and the MOSFET. Though he had the patent, Lilienfeld didn't publish any of his research, and even if he did, it likely would have been pretty difficult for one man to go up against the established tube industry. 8 years later, German physicist Oscar Heil filed a patent for a device very similar to Lilienfeld's. But like Lilienfeld's invention, Heil's seems to have gone largely unnoticed. Years later, Bell Labs assembled a team of researchers to develop a proper replacement for vacuum tube technology. In 1947, researchers John Bardeen and Walter Brattain built a point contact transistor using germanium. Their prototype is widely recognized as the first transistor. Though it looks a bit like something out of a sci-fi movie, the device's construction is relatively simple. Like all transistors, the device has 3 leads. One connected to the germanium crystal at the base, and 2 more constructed of gold foil, held in place with a spring. Now, in order for this thing to work, the 2 foil contacts needed to be very close together. Too far apart, and the crystal wouldn't conduct a signal. Brattain had a clever solution for this problem. He mounted a single piece of foil on a plastic wedge, and then separated it in 2 using a razor blade, Once in place, current only needed to travel a very short distance across the germanium surface. After learning of the discovery, project supervisor William Shockley began intensely researching a refinement to the invention and a place in the history books. What he came up with is referred to nowadays as the bipolar junction transistor. Bipolars are controlled by applying a current to their base terminal, which in turn controls the flow of charge between the collector and emitter terminals. The arrow in the transistor symbol indicates the direction that positive charge can flow. Now, just to make things a little more interesting, both FETs and bipolars are available in positive and negative type polarities. An NPN bipolar is like a switch, which is normally open. It won't conduct until a current is applied at its base terminal. PNP types, on the other hand, act in the opposite way. They reduce the flow in relation to their base current. Got all that? Good. Let's go make something that lights up. This is a relatively easy circuit to build, and it's pretty cool because it converts small amounts of conductivity to light. It's sort of like a pressure-controlled LED fader switch. Well, you'll see. To build it, you'll need a few parts. 3 resistors, a 220 ohm, a 1K ohm, and a 100K ohm. Also need an LED, 5mm one is good, a 2N3904 transistor, 9-volt battery, and a battery clip. Oh, and you also need some wire, too. That 2N3904, that's a bipolar junction transistor, NPN type. Of course, its leads correspond to the terminals we talked about in the schematic. From left to right, they are the emitter, base, and collector. You could always remember the order with a simple phrase like, "Eat big cookie," or something similar. Anyway, follow along with the schematic and make all the connections as it specifies. Be sure to connect the LED's shorter lead to the collector of the transistor, the 3rd pin. Hook up a couple of longer wires to act as your probes. Connect your 9-volt to the breadboard's power rails, and you're good to go. The transistor will amplify the small amount of current present between the 2 leads, and power the LED accordingly. You can use it to measure the resistance of different substances like skin, water, or even a big cookie. If you're looking for more good transistor info, check out the following sites. And for all the latest in DIY, home built, and handmade, go to makescene.com. Thanks for watching.